All right. Thank you for the introduction. And yeah, today I want to talk about uh, some approaches for modeling durability problems with Endurica. The Endurica solvers are compatible with MSC Mark. And what I want to show you today is, a lot of times people have said that solving um, durability problems with elastomers can be a tricky problem, and part of that is because the material behavior of rubber is nonlinear, and there are a number of um, special effects in rubber, temperature effects, rate effects, strain crystallization effects, and the tools that we're going to show you have been purpose developed specifically for rubber using techniques that are able to make accurate predictions for life in rubber under field usage. Just a quick introduction to Endurica. Uh, the company was founded in 2008, so this is year number 14 for us, and our entire focus is on developing CAE solutions that allow you to predict the durability of elastomer parts. I'm going to talk about the technology that we've developed, but it's very unique, and it's been successful enough that if you look at the Rubber and Plastics News list of top 9 global rubber part suppliers, 6 of them are using Endurica solutions today. So we've had a lot of success in penetrating into the market in the rubber industry. Last year, we won it's called the Tibbets Award, which is an award that's given to engineering firms that are commercializing technology. We have 3 fatigue solvers, and each of them is focused on a slightly different task or a slightly different workflow. So let me introduce these solvers, and then in my talk, I'm going to give you examples of how each of these can be applied to solve different types of analysis objectives. The first solver, Endurica CL, that is our original solver, and it's in some ways it's the simplest workflow. It is when you use Endurica CL, it's used in a post-process only mode, such that you would model your load case in Mark, and then you would export the stress and strain history from that time domain load case in Mark, and then Endurica CL could tell you for each element of the model how many repeats of the load case that you gave the part would endure. So very simple workflow, post-process only. That's Endurica CL. Endurica DT is our incremental solver. And the incremental solver allows you to compose sequences of many different load cases, right? So on day 1, maybe you have a certain load case, and on day 2, another load case, day 3, another load case. With Endurica DT, you can compile as many different load cases as you want. You can calculate residual life or residual strength if you prefer. Endurica DT allows you to use a co-simulation mode. Right, sometimes in rubber you have the combined effects of aging and fatigue, or cyclic softening and fatigue, and Endurica DT can couple with a finite element code, and so that your finite element calculations can update the stress strain fields as part of the durability calculation. So very powerful, flexible tool for incrementally defined problems. If you're using block cycle schedules, for example, in the automotive sector, you could use Endurica DT to model that. The final tool is what we call Endurica EIE. That's an acronym that stands for Efficient Interpolation Engine. And the reason you need EIE is because sometimes you're in a situation where it's important to be able to calculate fatigue under the action of road load data, right? You go to the track, you make a recording at say 1,000 hertz on your data acquisition system, and you come back with a history that's maybe 2 million time steps long. That history is much longer than you're going to be able to analyze in a direct finite element run. So what you can do is you can use Endurica EIE to pre-compute some representative solutions of the part operating in different states. And then EIE can interpolate from your pre-computed solutions to generate the strain history from your road load data. It's very fast. We've benchmarked it at about 10,000 times faster than the finite element, than the direct finite element method. And so it opens up the possibility to look at real-time road loads, and it is fully nonlinear, so it's able to, it's very appropriate for the rubber analysis. So these three tools together provide a very complete solution that can solve just about any durability problem you want to put to it. So let's, well, I guess first of all, let's talk about the different kinds of durability analyses that people typically want to do. And there's 4 categories. These are kind of textbook categories. The first category are what we call infinite life types of problems, right? This is maybe the simplest level of analysis, where what we're trying to predict in the infinite life category, let me get a laser pointer here, right? So I'm talking about this first row here. In the infinite life category, we're not trying to predict how long the part might last, but we're trying to take advantage of the fact that rubber has a fatigue threshold, and we're just asking the question of whether the material is operating above or below its fatigue threshold. And what we can do is we can calculate a safety factor that indicates the margin by which you are operating below the fatigue threshold. So it's very simple analysis. And what this means is that you don't have to characterize the material very deeply in order to make predictions, right? You just need to know the intrinsic, you need to know the fatigue limit for your rubber. You need to know the crack precursor size of your rubber. Endurica is based on a fracture mechanical calculation that requires knowledge of the precursor size of the rubber. And if you know those 2 things, then you can calculate safety factors. The next level of analysis, if your safety factor is less than 1, that tells you that the life is not going to be infinite, but it doesn't tell you how long the part will last. And if you want to answer that kind of question, then you need to go the next level deeper, and that's what we call safe life analysis, where you give me a load case and I calculate the number of repeats of that load case that it takes to fail the part, and then I compare that failure prediction to the design requirement, right? Maybe I need to show that the part will last for 5 years or 10 years. And with a safe life approach, I can calculate the number of repeats. I can compare that to my requirement, and then I'm good. So that's the safe life approach. Now, in the next level deeper after safe life is what we call the damage tolerant approach. And in the damage tolerant approach, you begin to think about things like monitoring the damage, right? Inspection types of questions. And from a computational point of view, you can think about tracking how damage develops transiently in the material as you apply more and more load history. And so for example, maybe you're looking at residual life or residual strength, and that's what we would call a damage tolerant approach. And then finally, there's also what we call the fail-safe approach, and that's where we say, hey, look, the the part is guaranteed to fail at some point. Let's arrange things so that when it does fail, there's ways to mitigate that. And there's a number of approaches to that, but one of the approaches is to implement a digital twin where you monitor loads in real time, you accrue damage in real time, and you have a dashboard where you can track the evolution of damage in your part. And so all of these different types of problems are supported by our solvers. You can see here, I've sort of made a little matrix here that just indicates, right? So for the first two levels, infinite life and safe life, that's really where Endurica CL would find application. If you're going to start doing block cycle analysis, if you're going to start looking at incremental damage accrual or residual life types of problems, if you're going to do a digital twin, these are all applications where you would use our DT solver. Now, in any of these applications that require that you work with road loads, then you're going to use the Endurica EIE to generate your strain history. Now, of course, if you're going to run durability simulations, it's really important to properly represent the material, right? If you're using a fatigue life prediction that does not capture all of rubber's special effects, you're very likely going to make very poor predictions. Our modeling approach is designed to be very scalable. We start with some basic information about the material. You need to know your hyperelastic stress strain law, and as the earlier talks were addressing. You also need to measure what we call the core fatigue parameters. So we use a fatigue crack growth rate curve, and we use a measurement of the size of crack precursors in the rubber. And based on that information, we are able to, that's sort of the bare minimum information you would need to do a fatigue calculation. Now, many times there are situations where there are additional material effects that need to be taken into account, right? For example, if you have large temperature gradients in the material, it's important to define a crack growth rate law that reflects that temperature dependence. So we have a set of thermal measurements that we can do to define the temperature behavior of the crack growth rate law. Under conditions where you have a mean stress or what we call a non-relaxing cycle, right? Think of an engine mount where you have a static load on which is superimposed dynamic cycles. Some rubbers can exhibit an effect called strain crystallization, and it can affect the fatigue life by a factor of 1,000 or 10,000. And in that case, it's necessary to characterize the strain crystallization effect and include that as part of your analysis. And so we do have material models that support this, as well as ways to characterize that experimentally. We can also measure rubber's fatigue limit, right? We call that the intrinsic strength. And then there's also other, now these, I would say these in the middle row here, these are very common effects. You don't always need them, but very commonly they come into play. And then we also have advanced effects where we can look at cyclic softening. We can look at the effects of a heat exposure where the material properties are evolving in time. The Endurica code does include an Arrhenius-based aging model for both the stiffness and the fatigue crack growth rate properties. So you can have combined aging and fatigue going on in your material. Our material models allow for time-dependent creep crack growth to occur. And we can also do a characterization of the distribution of crack precursors in the material so that we can make statements about reliability of the part. Now, so let's talk about some examples. I'm going to briefly go through 4 applications, and like I said, I've arranged these in order of let's say depth of analysis, right? So the infinite life is the simplest analysis, and you might use that in a scenario where you're analyzing a part that is a very cheap part. So we're going to look at a grommet, right? A rubber grommet. It's just a tiny little rubber part costs 50 cents. And in that case, you don't want to do a very detailed material characterization because that can be expensive and time consuming. So what we do instead is we simply measure the hyperelastic parameters. We measure the fatigue limit of the rubber, and we're going to use Endurica CL to calculate safety factors on the grommet, and that will give us a go, no-go indicator. It also gives us relative information to compare two different designs, and that's a really good way to go for a very simple application. Now, another application from the automotive sector would be, we're going to look at a sway bar link. Now, in this case, because the bushings are made of natural rubber, because there is a permanent load that's carried on this part, it becomes necessary not only to look at the stress strain and the core fatigue behavior, but it's also necessary to characterize the strain crystallization effects in natural rubber. And we're going to look at this under the action of road loads. So in this case, we're going to look at using both the CL and EIE solvers together. Now, for a bushing, it's very common that the customer who is the OEM is usually going to require some sort of block cycle schedule for the bushing to pass. And using Endurica DT, we can model that block cycle schedule. And in fact, we can include, in addition to strain crystallization, we can include the effects of if there's self-heating in the rubber, if there's aging of the rubber. Those are all effects that we can incorporate as part of the analysis to make a very accurate prediction. Finally, the last example is, I'm going to show an example that we did. We collaborated with a company that builds data acquisition technology. TrueLoad is the name of the company. They can measure the loads on a part. And we actually built a prototype of a digital twin using a pogo stick. And I'll show you that example in a very summarized form, but basically showing how the tools are fast enough and good enough that we can actually do these predictions live based on sensor readings that are coming in from a system. All right, so here's my grommet example. In this case, this is made of a chloroprene filled with 50 parts per 100 of rubber of N330 black. It has a shear modulus of 3 megapascals. It has a crack precursor size of 0.1 millimeters, and it has a fatigue threshold of 800 joule per meter squared. The Endurica solvers are all based on a technology called critical plane analysis. And the idea in critical plane analysis is that cracks are able to, oh, wait a minute here, let me get this animation going. How do I, there we go. So the idea is that cracks can occur in any orientation in the part. And so in order to make a fully conservative and fully accurate prediction of the life, it's necessary to consider the life that would happen at any point for all possible crack orientations. And then the life is based on the crack orientation that gives you the shortest life. Now, when we apply this for safety factors, we're not calculating life, we're just calculating the ratio of the fatigue limit to the maximum value of the tearing energy of the worst crack in the part. And this sphere represents, we've colored the sphere according to the safety factor. Right where you see red, that is the place where the safety factor is the lowest. Where you see blue, that's where the safety factor is the highest. If there is going to be a crack, it's going to be oriented with its normal in the direction of the red spot on that sphere. So that's the prediction that we make. The fatigue limit T0, that's just defined as the bottom end of the crack growth rate curve, right? So if you plot the rate of crack growth as a function of the input tearing energy, and if you look at the crack growth rate curve, there's a bottom limit. That bottom limit is the fatigue limit that we use for purposes of calculating this safety factor. Here's an example of what that looks like. This is the grommet that I mentioned operating under a load case that has, both X, Y, and rotational motions specified. And in this case, the color contours you're looking at are colored according to the safety factor. Where you see black, that indicates that the safety factor is less than 1, indicating the life will not be infinite. Where you see red colors and anything cooler than red, then that indicates that the safety factor is 1 or greater than 1. And in those locations, we can expect indefinite fatigue life. Again, in this case, we're predicting that the part is going to have a finite fatigue life, and the failure is going to originate at this spot here where you see the black in the contour image. So very simple analysis, does not require a deep characterization of the material, but the limitation is that we know the life is finite, but this does not tell us how long the part will last. If we want to know that, then we would have to go to the safe life approach, and then we would have to look at the full crack growth rate law and calculate a life. Let's look at another example. This is a sway bar link bushing, and it's loaded axially. The material characterization for this obviously has to be more sophisticated, because not only do we need the fatigue limit, but we also need the fatigue crack growth rate curve. So what you're looking at here is so this chart is the stress strain characterization, right? The hyperelastic law. This chart here in the middle, this is the fatigue crack growth rate law that's used to describe the damage behavior of the material. The bottom chart, this is the strain life curve, and we use this curve to calibrate the crack precursor size. So you can actually calculate this curve based on the crack growth rate curve, assuming that you know the precursor size. We use the precursor size as a curve fit parameter, and when you get good agreement between the nucleation experiments and the crack growth experiments, that tells you that you've properly calibrated the size of your crack precursor. In this case, we've calibrated it to a size of 12 microns. Now, this is a natural rubber part, and what you're looking at here is a map. Some people call this a Hay diagram. The x-axis is the mean strain, the y-axis is the strain amplitude. The colors are indicating the fatigue life at each combination of mean strain and strain amplitude. And what you can see here is the effect of strain crystallization on the Hay diagram, right? There are places on this diagram where if you increase the mean strain, the fatigue life goes up, which is, if you try and use a metal fatigue approach to predict fatigue life, you are going to make very, very wrong predictions of the life of the rubber. It's imperative that you account for the strain crystallization effect, and that's what we're doing here. So now that we've got the material characterized, we can let's look at a road load history. In this case, we're going to use EIE to look at a load history that involves a single channel of loading. EIE actually is capable of looking at up to 6 input channels. So if you have 3 forces and 3 moments, we can use the same approach for that. But to keep things simple here, we're just going to look at a single channel of loading, just the displacement in the axial direction on the sway bar link. Now the way this works is with Endurica EIE, rather than attempting to model this entire random vibration in MARC directly, what we're going to do is we're going to use MARC to model this load case here that I'm showing on the right-hand side, right? So this basically has 8 points that go from a displacement of 0 to a displacement of 4 millimeters. And we call this our map, right? So we're basically tabulating the solution or pre-computing the solution at 8 points. And then what EIE does is it uses these 8 pre-computed points to interpolate the values of the solution at all of these other points. So, right, if I need to evaluate this curve here, I'm just going to come over here on the map and I'm going to interpolate between those 2 points. If I want to evaluate the curve here, I'm interpolating between these 2 points. Interpolation is a very fast calculation. And so this, like I say, we've benchmarked it at about 10,000 times faster than a direct finite element analysis. And it gives answers that are really the same as what you would get with a finite element analysis, so long as your map is sufficiently discretized, of course. So here's an example. If we take the strain history that we calculate from that and pass it into Endurica CL, then we can calculate contours of fatigue life on the link. Again, we're using this concept of critical plane analysis. That's the sphere that you're seeing here. This is a representation of, now in this case, instead of calculating safety factor for all of the different possible crack orientations, here we're calculating the fatigue life of each crack orientation. And that fatigue life is calculated by integrating the crack growth rate law from the initial crack size to the end of life crack size. And the plane that minimizes the life is the predicted failure plane. One of the limitations of methods that are based on a Voller curve, right? If the metals fatigue people sort of pioneered the use of these Voller curves for fatigue life prediction, but for rubber, Voller curves are very problematic. One of the problems is that they assume that the fatigue life is predicted by the maximum principal stress, which is true in certain cases, but it's certainly not always true. In simple compression, that breaks down. When you have a strain crystallizing material, that breaks down. Critical plane analysis is the method that allows you to correctly predict those effects. Let's look at another example. This is a control arm bushing that's going to be operating under road loads with 3 input channels. Again, we're going to use our EIE tool to simplify the analysis, speed it up. In this case, we're going to do the hyperelastic, the core. We're going to do the non-relaxing, and I'm not really going to talk about this, but we certainly could, model the aging and thermal effects in here as well. In the last example, I showed an example where we were running the an analysis with a single channel. In this case, we have 3 channels, and this animation is showing the analysis that we would do in Mark in order to generate the 3-dimensional map that represents the load space that the part is operating in. So basically, we're scanning through every possible load state that the part might take as it runs through its road load signal. And once we've pre-computed that map, now we're ready to do the analysis of the road load. And if I go to the next slide, you can see the animation here of this map, and I'm playing the road load into that map, and we just interpolate from that map to get the strains that we need to do the fatigue analysis. So we're going to take the results from EIE, pass them to Endurica CL, and what we get is a prediction of the fatigue life, in this case 36,000 repeats of this signal. So that's a capability that we have with EIE and CL. I also want to talk briefly about the incremental analysis, right? So with CL, you're just predicting repeats of a given load case. That load case can be as complicated as you want, but it's just repeated ad infinitum until end of life. With Endurica DT, you can model a block cycle schedule. So for example, you could say, there's a first load case that we're going to call step 1, run that for a certain amount of time, stop the analysis, restart the analysis, and maybe when you stop the analysis here, report the residual life or the residual strength in the part, but then do a second step of analysis for another period of time, and then do a third step. And in this way, you can accrue many different load cases. This is also the method that we use to update the material properties, right? Maybe in the first year, you have one set of material properties. Due to aging, in the second year, you have another set. In the third year, another set. And the incremental analysis allows you to account for the evolution of material properties with cycles or with time. So now what this is a comparison of the control arm bushing under road loads and under a block cycle schedule. Endurica has a feature that allows you to extract a block cycle. So if you give it a road load signal, it will extract a block cycle schedule from that signal that you can use in your testing efforts to simplify the test. And what you're looking at here is a comparison of the life that's calculated from the full road load signal with the life that's calculated from the block cycle that's extracted from the road load signal. And you can see they produce a very similar failure mode, and then they also produce a very similar fatigue life. The last example I want to talk about is a digital twin. So here's a picture of Tim Hunter from the TrueLoad guy, and he's jumping on this stick. This stick is instrumented with strain gauges such that as he's jumping on the pogo stick, he can actually in real time record. There's a data acquisition, I don't know if you can see it, there's a data acquisition system here strapped to the handle. And so this thing can actually measure in real time the loads that are occurring in X, Y, and Z, right? He's measuring 3 channels of loading, X, Y, and Z. There's a vertical, and then there's 2 translational loads that are being measured. And those are being measured in real time with the TrueLoad system. That load history is then passed into Endurica EIE, right? This chart shows an example of the loads for a series of jumps. Those get passed to EIE on a periodic basis, right? So we acquire some data, we pass it to EIE, we get a strain history for every element, we accrue the damage using Endurica DT, our incremental solver, and then what you can do is you can actually create a dashboard where you show the actual current damage state of the part. This counter here is showing the residual life in this pogo stick has a rubber tip. And so we've done a mark analysis of the rubber tip, and that's encoded in this digital twin, right, because that's what we use to generate the map for EIE. And so we're able to calculate this residual life, and as you're jumping on the pogo stick, that residual life is decremented according to the actual load history that has happened in the part. Here's a closer look at some of the details there. This is the mark analysis that we did to generate the map. If you, now this is kind of the nominal load case. If you do this nominal load case, the tip will endure about 170,000 jumps. So that's kind of the initial, right? The residual life at time 0 is 170,000 repeats. Now, as you start to jump on the stick, this life is going to decrement depending on whatever loads are going into it. And here's an example for 3 periods of updating, right? We're going to feed in a load history, the solution gets updated, feed it in again, it gets updated again, and this just goes on and on with whatever load cases come in. If you look at the color scale, you can see that the crack, this is showing you the length of the crack in each element, and you can see that crack is growing in the worst element. The speed of the computation, it takes about 2 seconds of compute time for every 20 seconds of load history that we're passing in. So this is very much a real-time calculation, which is suitable for digital twin implementation. So yeah, that's 4 examples of different levels of analysis that you can do with this. So, you know, our solvers are the most complete, the most scalable, the most accurate fatigue life prediction system that you can get anywhere. Like I say, 6 of the top 9 rubber companies in the world are using these tools. It's based on this concept of critical plane analysis, which is just the idea that cracks can happen anywhere and they can happen in any orientation, and we have to consider all of those possibilities. It's a workflow that's proven across many different applications, right? Anyway, as simple as infinite life analysis all the way up to a full digital twin. These tools are integrated with MSC Mark, you know, whereas people used to say this was a hard problem to do rubber fatigue, not anymore. You know, use our tools and you can get durability right. So thank you, and I can hang around for some questions if there's time.